Okay, can you guys hear me and see me now? Namita, nice to meet you. Divya, nice to meet you. James. Okay, great. All right, welcome everyone. My name is Sam, or Samah. I'm an F2 working in South London. Hope you're all doing well. Thank you so much for joining me. Welcome. Hi. So we are going to be starting the second part of the evidence-based medicine crash course. We've done the first part yesterday, and there's also an introductory session that was done in January. Maybe some of you have attended one or both of these sessions. It's okay if you haven't. The recordings are available on Medall. And before I get into the topics that we're going to discuss today, I'm just going to do a quick recap of what I've covered in the introductory session, just so that everyone is up to speed. So I'm going to start by sharing my screen. We're going to go from there. Okay. Okay. All right, before I continue, are you guys able to see the first page of this presentation? No. Oh, I see. Okay. Okay, I think it's available now. I think you guys can see it fully, right? Yeah. Okay, fantastic. All right, so welcome everyone. Today we're going to be covering the second part of our series. It's going to talk about the ABCs of statistical analysis and epidemiology. I realize it is called ABCs of statistical analysis, but this session in particular is going to be heavily based in epidemiology. I know that maybe a lot of you are like me in medical school. I found this topic to be quite tricky, and it was very frustrating to study. So I wanted to put in quite a bit of information here just to make it a bit easy to understand. It's not as hard as I thought it was, so hopefully you guys would be able to appreciate that as well. Okay, so the agenda for today, I'm just going to talk a little bit about our competition for those of you who are new in terms of our journal club series. I'm just going to give a bit of a crash course to give you some basic information, and hopefully it'll give you a bit of a head start so that you can participate in our competition. And I'm going to talk a little bit about that. I'm going to give a quick recap, and then I'm going to get into the epidemiology. It's going to cover some aspects of bias, and we're going to do the statistical analysis, and then I'm just going to talk about what comes next. Okay, so obviously taking part in a competition like this has a lot of advantages for anyone who is watching. It can help build your CV. If you're working at any point in your career, at some point or another, you may have to do a presentation at work in terms of journal club. So this particular presentation is going to help you understand the different research papers that you come across in terms of common terminologies and its implications. So it's going to help you out in your work. It's going to build your CV. It's going to give you a competitive edge for training posts. And of course, it's going to help you out should you decide to join in our competition. And of course, the more the merrier. In terms of the details of this competition, is going to be available on our journal club page at mindthebleep.com. It's going to have the details on how to submit, when to submit, important dates, and of course, once our winners are announced, they'll be posted in our website, of course, with their consent. We want to make sure that as many people get I want to make sure that everyone gets the most out of this. So people who win first place are not going to be our only winners. We will also have some runner-ups that will have an opportunity to present their presentations as well in other sessions. But the finalists, the difference is the finalists will be, we'll have a group of them, and they will be the ones who will then, they'll be the finalists who will then become, will be picked to be the Journal Club's national winner. And of course, if a finalist is unable to participate, in that case, the next runner-up will take their spot. So, of course, our finalists and our runner-ups will all get certifications and awards. And so, yeah, it's a really great opportunity. And I think it's great to give it a go. Doesn't matter how much experience you have, whether it's little to none or a lot of experience, it's just a great opportunity to partake. And not only for the people who are presenting, but the people who are watching and participating, they get to learn a little bit as well. Okay, went on a little bit of a ramble there, apologies, but now we're going to go into our quick recap. So Journal Club, again, are regular meetings in which healthcare professionals discuss and review recent research articles from medical journals. As you know, medicine is a very fast-paced specialty. There's a lot of things that take place and a lot of changes in terms of guidelines. So the Journal Club is a way to help us stay up to date in terms of our medical knowledge. There's a lot of benefits, as you can see, encourages critical thinking, improves knowledge, opportunity for peer review, enhancing communication, and identifying gaps in our current knowledge and research needs. So there's quite a bit that you can gain out of it. So any presentation in Journal Club has a certain skeleton or flow chart. So the first part is a clinical encounter. So this may be a case that you may have seen at work or something that you may have heard of, and you have a question in regards to this case. Of course, when you are presenting, make sure that you have the consent of the patient and you anonymize this patient. So don't put the patient's information out there. But it's just basically for the learning point. That's why these journal clubs are made. Our session yesterday focused on developing the clinical question and the different study designs that are associated with it. You can definitely check it out after our presentation today. Our section as well is going to focus a little bit about the literature search as well. So in terms of understanding it. So we're going to start off with epidemiology. Here I'm going to talk about the different types of biases. I'm also going to talk about incidence versus prevalence, which is something that you may come across quite frequently. And it is the bread and butter for quite a few different concepts. So if you understand this, it'll make things a lot easier for you in the long run. Okay. Of course, there are many, many different types of biases. The ones that I've included are some of the most common ones. So in your own time, if you want to learn about more, you can do some of your own reading. But I've included 4. So this is our first one. Selection bias. This occurs when there's a systematic difference between individuals or groups that are selected for study participation and the target population. So just looking at an example of this, let's just say that you have a weight loss drug, and you want to test the efficacy of this drug. If you were to conduct a study where you have a control group and an intervention group, the control group will get a sugar pill, for example, a placebo, and the intervention group will get this weight loss drug. Okay? If you were to select people who are active in the gym, working out, and are very physically fit in your intervention group, and then select a random group of people for the control group, this would be considered a selection bias because these groups are not equal. They're not the same. Not everyone is it's not going to be equal between both. It's going to introduce a bias. This is the selection bias. So the bias here is in terms of your sampling. If you were to conduct this study in a more proper way, you would select random people from a population and then divide them equally into your intervention group and your control group, right? The control will receive a placebo, the intervention will receive the weight loss drug, and you monitor them over time. This is what we discussed in our last session, and this is what is known as the randomized control trial. So the problem with doing this is that it can basically lead to a false result. So an over or an underestimation of the true effect of an exposure or outcome. Does that make sense so far? Does this make sense? Okay, great. Wonderful. Measurement bias are systemic errors in the measurement or assessment of a study variables. Basically, in any study that's conducted, for example, like the one we have here, the randomized control trial, you may give an intervention group a weight loss drug and a control group the placebo. What people would normally do in order to reduce the amount of bias is that they will blind the participants and maybe even the researchers. So they won't tell, for example, specifically the participants if they're in the intervention or the control group. That way, when the participant is thinking about it or thinking about their progress, you want to reduce the amount of bias that they're taking into account. And the same thing for the researchers. If the researchers are assessing data and they don't know if these participants are in the intervention or control group, this reduces the amount of measurement bias. It's very similar to the concept of detection bias, but bias from the aspect of the researcher. Okay, we've got a couple more. So confounding bias is when there's a third variable, also known as a confounder, which distorts the association between exposure and the health outcome. And it's usually the only factor that differs between an exposed and exposed groups. So what do I mean by this? Let's look at an example over here. So you have a population of people who drink a large amount of coffee. I'm definitely one of those people. So if you drink a lot of coffee, studies have shown that it's associated with cardiovascular disease. Okay, so if you wanted to conduct a study and this is what you're looking at, you may not take into account that some of these individuals who consume large amounts of coffee may also be smokers. Okay, so smoking has a strong association with high coffee consumption, but also with cardiovascular disease. So this is a variable that's unaccounted for in this study, which is what I've highlighted in this box, that could affect your results. And this is what is known as a confounding bias. It's a variable that is associated both with the intervention as well as the outcome, okay? And it can result in misinterpretation of association. Another type of bias is attrition bias. When there is any kind of study that's being conducted, a lot of the time, not all the participants who initially start in a study will be there at the end. Some people may drop out, and some others may unfortunately pass away. So at the end of the study, what you may have started initially with 1,000 participants, you have 500 in your control and 500 in the intervention. By the end of the study, you may only have 421 in the control, and in the intervention, only 209. So those who are lost to follow-up and not included in the study leads to what is known as the attrition bias. So the difference in the number of people within a certain group can definitely affect the values. You may have heard that in studies, the larger the sample, the more accurate the results. This is also taken into consideration when we look at attrition bias. And also the differences between the groups as well can add some unwanted variables that could affect the interpretation of a study, and this is known as attrition bias. So in order to reduce this, you also want to include those that are lost to follow-up. Okay, so we've covered the four really common types of biases. I'm going to talk about incidence versus prevalence. So over here is what is known as the epidemiologist's bathtub. Okay, so you have your shower, it's pouring the water, and the bathtub is filled with water. Okay, this bathtub is cracked. There's some water that's dripping, and if we were to take the water as, for example, the population, okay, um, and this is the population that has a certain condition. Some may be lost to mortality, and some may have recovered. Okay. Let's take a look at the incidence. The incidence is the number of new cases that are occurring, which is why the water is pouring in. So it takes into account how quickly a disease can develop. It's useful in detecting rising transmission rates, and it can be used in decision making regarding necessary public health interventions to mitigate the spread of a condition. Okay. Prevalence are the number of cases that are already present within a given population, right? So they're already afflicted with an illness, either at a particular instance, at a particular point, which is known as point prevalence, or across a designated time frame, which is known as a period prevalence, okay? So the prevalence takes into account new cases as well as pre-existing cases, whereas the incidence only takes into consideration new cases, okay? The prevalence helps us to determine the burden of a disease within a given population, and it's used by public health for service planning. Okay. Before I move on, any questions so far? Any questions? Who's done with the elderly? Yeah. So Divya is asking, would you say studies done with the elderly population tends to have attrition bias most of the time? It can, most definitely. The elderly population obviously does have a lot of patients who are elderly tend to pass away, so there is quite a bit of attrition bias there. Yeah, so certain populations will have it more than others. But it can also take into account certain conditions as well, those with high mortality rates. Can definitely take that into consideration. Yeah, excellent questions. Yep. Alzheimer's disease, Parkinson's. Yeah, most definitely. Yeah, definitely. Yeah, okay, good. Any other questions? No worries. Okay, great. So now we're going to talk about measures of association. Could you explain the measurement bias again? Yeah, of course. I'm just going to go back to that slide again. So measurement bias takes into account, so measurement bias basically is where if you were to conduct a study, for example, we'll take the weight loss drug. Let's just say that you're a company, you've made a weight loss drug and you want to advertise this drug and you want to say, okay, this drug causes a great amount of weight loss and it's great. Okay. In the study, you have a population of 1,000 people. Okay. You've recruited 1,000 people. 500 are in the control group, so you've given them a sugar pill, and 500 are in the weight loss group, weight loss drug group. So let's just say in the study, you did not do any blinding, which means you've told every single participant and researcher who is in which group. So for example, you'll tell participant A, okay, you'll be given the placebo or the sugar pill, and participant B, you're going to be given the weight loss drug. Okay, so as the study continues and as the study goes on, yes, there are things that you can take into consideration, like the patient's weight loss, like the measurements that are difficult to misinterpret. But there are certain other factors. So a patient might say in the placebo group, not the placebo, the weight loss group, yes, I have been noticing that I'm losing weight, but they haven't, you know. So that's something that they may be looking into account. Or better way to explain it is from the researcher's perspective. So they'll say, oh, you know, I've been noticing within the intervention group, those who are taking the weight loss pill tend to be losing a lot more weight. So you're focusing more on one area compared to another. And you may not be taking into account maybe the control group. So it has a lot of similarities with detection bias, right? So detection bias is where you say, oh, you're paying more attention to one group compared to another, and that can lead to measurement bias. So these are differences that you don't take into consideration. And these things, measurement bias can occur consciously, so people sometimes can make a conscious effort to do this, or subconsciously. Does that make sense? If not, no worries. I can explain it again with a different example if you'd like. Oh, okay, great. Okay, so, all right, measures of association. So for this one, I'm going to be talking about smoking and lung cancer, and I'm going to be using this to explain the different concepts. Okay, relative risk. So, relative risk is a measure that's used to quantify the risk of an outcome in one group compared to another group. So relative risk is a ratio. Okay, take into consideration this is a ratio of the risk of an outcome, which in this case is lung cancer, in the exposed group. And when I say exposed with our example, we're talking about smoking. Okay, so outcome is lung cancer. The exposure is exposure to cigarettes or those who are smoking. Okay, so it represents a ratio of the risk of an outcome, the risk of developing lung cancer in the exposed groups, in those who smoke, to the risk of developing lung cancer in the unexposed group. So in this case, if we were to look at this particular box, we have a population who smokes. Their risk of developing lung cancer is 20%. These values are not backed by science. It's just to help solidify the concepts, guys, okay? So we'll say smokers have a 20% chance of developing lung cancer, and non-smokers have a 5% chance of developing lung cancer. So we say the relative risk is 20% divided by the 5%, which means the relative risk is 4. And remember, this is a ratio. So you've determined the relative risk of developing lung cancer in those who smoke versus those who don't smoke. So what do you do with this value now? Well, you can divide the relative risk values in those that are below 1, above 1, or equal to 1. So if you get a relative risk that's equal to 1, so for example, if those who smoke 20% develop lung cancer and those who don't smoke also have a 20% chance of developing lung cancer, our relative risk will be equal to 1, in which case the risk of the outcome, which is the lung cancer, is the same in both groups, which means there's no association between smoking and lung cancer. We obviously know this isn't true, but again, this is just to solidify the concept. Now, in the second point here, where the relative risk is greater than 1, which is what we have here, the relative risk is 4, the risk of the outcome, developing lung cancer, is higher in the exposed group compared to those in the unexposed group, which means there is a positive association. Okay? And if the relative risk is less than 1, okay, in that case, you can say the risk of the outcome, which is lung cancer, is lower in the exposed group compared to the unexposed group, which means there's a negative association, which means that you can also say that smoking is a protective factor against lung cancer. Again, not true, just to solidify the concept. So in this case, relative risk, smokers are 4 times more likely to develop lung cancer than non-smokers. Okay, so that's our relative risk. Those of you who may have attended yesterday's session, this may look a little bit familiar. For those of you who haven't, I'm just going to go over it quickly. This is just a bit of a chart to help for those of you who are visual learners to keep in mind an organized way of looking into different types of study designs, okay? So we have the case control, which are the types of studies that look for outcomes in the past, your cross-sectional, which look for studies in the meantime, and those that look for their outcomes in the future, or the cohort studies. So relative risk is something that is a measurement that is normally used in cohort studies, okay? It provides a measure of the strength of association between an exposure and an outcome, and it helps to assess the impact of an exposure of the risk of developing a disease. Okay, it's most commonly used in cohort studies, as well as randomized control trials to compare disease risk between different groups of individuals. So if you were to take into consideration a study where you have 1,000 people, okay, 500 of them are smokers and 500 of them are non-smokers. You follow them over time and see how many develop lung cancer and how many don't. This is a cohort study. Okay? And please feel free to stop me and ask questions if there's anything that's unclear. Okay. Oh, yes. I forgot I put the slide in. So it just comes to show you. It's a visual representation of what I was talking about. So you got the smokers, 20% develop lung cancer, non-smokers 5%. So 20 divided by 5 is 4, which is our relative risk, and this is commonly used in cohort studies. Okay, I'm just going to skip this for now. Sorry. So what we have here are case control studies. So these are studies that look back in time. Okay, so you have a certain outcome. You may have a certain population. Some of them have lung cancer, some don't. What you do is you take this population, you interview them, you look at the things that happened in their past, and you try to find an association between their development of lung cancer and something in the past. So you can say, wow, okay, we have a population of 1,000, 500 of them were smokers. We look back in time, 500 of them have lung cancer. We look back in time, most of them are smokers. And 500 of the people who didn't develop lung cancer, we look back in time, most of them didn't smoke. So there is an association between smoking and lung cancer. Okay, so this is a case control study. And for case control studies, you can use what is known as the odds ratio. Okay. If you've seen these terms before, then you know that it might be very difficult to tell the difference between the two, but please bear with me. After I explain the odds ratio, I'll discuss the differences between that and the relative risk, okay? So the relative, like how the relative risk is a ratio, odds is also a ratio, okay? It's a measure used again. We have our smokers that develop lung cancer and non-smokers who still develop lung cancer. So a study may have been conducted that showed that 1 in 5 smokers develop lung cancer, and 1 in 20 non-smokers develop lung cancer. So what are the odds of that? So the odds ratio is those who don't develop lung cancer, those who develop lung cancer who are smokers, which is 0.2, divided by those who develop lung cancer who are non-smokers. So the odds ratio is 4. So again, what do you do with this value? Similar to relative risk. If the odds ratio is equal to 1, the odds of the outcome, which is the lung cancer, is the same in both groups, which means there is no association between smoking and lung cancer. If the odds ratio is greater than 1, which is like 4 in our case here, the odds of the outcome, which is the lung cancer, are higher in the exposed group compared to those in the unexposed group, which means there is a positive association. And the third possible outcome is the odds ratio is less than 1, which means it's lower in the exposed group compared to those in the unexposed group. So what's the difference? When you calculate, let's just say that you have a scenario here where you're in a museum, okay? And there's 100 people. The dots represent people. I know there isn't 100, but just bear with me. So there's 100 people in a museum at a given time, okay? Out of the 100, one person coughs, okay? The risk of the risk of a person coughing is 1 in 100, okay? So that's 0.01. The odds is not the same as the risk. It's not 1 in 100. You take the one person and you subtract it from the total population. So it's 100 minus 1, which is 99. So the odds of a person coughing in the museum in this given time is 1 out of 99. Okay? So the values, the risk and the odd here are really similar. So where do you start to see the differences? You see the differences when the incidence of a condition is high. Okay? So in this case, the incidence is the cough. So since the incidence is low, it's only 1, the risk and the odds are not that different. But let's change it up a little bit. So same scenario, you're in a museum in a given day, there's 100 people, and as opposed to just one person coughing, 55 people cough. Okay, so the risk of someone coughing is 55 over 100, or 55%. Okay, the odds is 100 people minus 55, you get 45. So the odds are 55 over 45, or 1.22222, right? So there is a very big difference now. From before, where we went to 0.01 for risk and 0.0101 for odds, we went to 0.55 and 1.22222. So you see a difference when the incidence is higher. That's where you start to see a difference between the relative risk and the odds ratio. All right. This one is a pretty fun one, very straightforward. So we have our same case again. We say, for example, you have your non-smoking population. In a non-smoking population, the risk of developing lung cancer is 5%, right? There are other things that can cause it, but the baseline we'll say is 5%. Let's just say we have Mark here. He's a non-smoker. Mark has a 5% chance of developing lung cancer as a non-smoker. But let's just say that he does start smoking. In that case, his risk of developing lung cancer goes from 5 to 20%. As we know, there's more than one cause. There's more than one thing that can cause lung cancer. But our focus right now is about smoking. How much of this risk is attributable to smoking? That's what we know. That's what we refer to as the attributable risk. To calculate the attributable risk, we take the 20% of risk for those who are smoking and subtract from it the 5% who are non-smokers. And we find that 15%, okay, of the risk of developing lung cancer is attributable to smoking. Does that make sense? Does that make sense? Okay, great, wonderful. Okay, now we're going to talk about sensitivity, specificity, positive predictive value, and negative predictive value. Okay, so starting with sensitivity, this is a measure of the ability of a diagnostic test to correctly identify individuals with a given condition or disease of interest. Okay, so a highly sensitive test is able to identify a majority of positive cases, and a diagnostic test with low sensitivity can miss out on positive cases. Okay, so for this section, for this coming section, I'm going to be using HIV as the condition, and the test in terms of sensitivity is our ELISA scan, And for specificity, we're going to be using Western blot. Okay? So let's just say that we have an ELISA scan for HIV, and we say that it has 97% sensitivity. What does that mean? If we have 100 dots here, and each dot represents one individual with HIV, we have 100 people here with HIV, and every single one of these people, we do an ELISA scan for them. 97% sensitivity means that the ELISA scan is able to correctly diagnose 97 out of the 100 with HIV, which means that 3 out of the 100 will be given a false negative test. So they are HIV positive, but the test will falsely say that they're negative. Okay? So again, HIV, but this time we're looking at specificity with a Western blot test. So specificity is a measure of the ability of a diagnostic test to correctly identify individuals without a given condition or disease of interest. So a highly specific test is able to identify a majority of negative cases, and one that has a low specificity can miss out on negative cases. Okay? Let me explain this with our example. Again, we have our 100 people. Okay? These are people that don't have HIV, so they are not HIV positive, and we do a Western blot for all of them. Okay? And we say a Western blot test has a 97% specificity. It means that out of the 100 people that are truly negative for HIV, the Western blot test is able to correctly say that 97 of these people do not have HIV. It means that 3 out of the 100 will not have a diagnosis of HIV, but will be given a false positive test. So they'll be told, you do have HIV, although they don't. So that's our specificity. So a lot of the times you may be wondering, okay, in that case, if we have a test that is 100% sensitive, or a test that is 100% specific, why do we need to worry about the latter? Like why if we have a test that's 100% sensitive, why do we have to be worried about a test that's specific, and vice versa? This is because if we have a population of 300, okay, so initially we were testing 100, we have a whole population now, and the test, as opposed to being 97%, is 100%. Okay, if we have this population and we say, okay, those of us who don't have HIV can be incorrectly given a positive result. Okay, so this is looking at specificity. So if a test is 100% specific, okay, or more than that, you could say, oh, okay, like a lot of people are negative, but those who are negative may be given a positive result. Okay, so someone who isn't HIV negative and you have a test that is, you just do one test, they may be told, oh, you're HIV positive, and they're not. And this can introduce a lot of problems if you look at it clinically. It creates panic for the patient, okay? And those that are healthy can be treated for a condition they don't have. It's an unnecessary waste of resources and time. Does that make sense? Any questions? No? Okay. And again, the opposite is true. So if you have a test and you say, oh, if you have a part of a population with HIV, they may be incorrectly given a negative result. So they're told, oh, you don't have it, but they do have it. And again, this gives the patient false hope or a sense of security. And take it again. You want me to repeat the last part again, this one? Okay, so what I'm trying to explain in this in these two slides here is that if you have the medicine is not a perfect science. So if you have a test that will detect everyone with a given condition, it can also falsely give positive results for those who don't have the condition. And again, if you have a test that is able to correctly identify everyone who doesn't have a condition, it can also give negative results for people who do have the condition. Okay? Yes. So the problem with relying on a test that is highly sensitive only or highly specific only is that there's going to be a portion of the population who's going to be given a false result, whether it be false positive or false negative. And that can result in, if it's a false positive, negative panic for the patient and a waste of resources if you decide to treat it. And if they're given a false negative result, then they won't seek the medical attention that they need. And obviously their health is going to deteriorate, and it's going to be very problematic, right? Which is why, in this next part, I explain that if you have tests that are highly sensitive and highly specific, the best thing to do would be to combine the two. Okay, so usually what would happen in patients who we're testing for HIV, we will start with a highly sensitive test, which means this test will be able to take into account as many people as possible who are truly HIV positive and give them the result that is positive. But that means that there are people who don't have HIV who may have a false positive test. Okay, those who are truly positive or have a false positive test, anyone who tests positive in the ELISA scan will then undergo another test through the Western blot. And this is a highly specific test. So in this test, it will confirm which patients don't have the condition. So you want to combine the two test results in order to get the most accurate outcome. And this might look a little bit familiar because it's usually put into this graph right here. So I'm just going to talk about the different constituents of it. So what we have here is a bell curve graph. This line, the continuous one, everything that's underneath it is considered true negative. So again, carrying on with our example, over here is a population that is truly negative for HIV. In this second bell curve over here, the dotted line, this one, all the population underneath it would be considered a true positive. So those are individuals that are HIV positive, okay? And in the middle here, these are the ones that are considered a little bit inconclusive. So, but just disregard that for the meantime. I just want you to focus on true negative, true positive, okay? These red lines represent the different tests, okay? So line A is supposed to represent a test that is 100% sensitive. So let's think about the ELISA scan. Let's just say that this ELISA scan is a test that has 100% sensitivity. What does that mean? It means that anyone who is truly positive is accounted for. You can see here, the line A and the dotted line doesn't go past it. It doesn't go behind it. So anyone who is positive in 100% sensitivity ends up getting the correct result. The downside of this, like what I was mentioning earlier, is that there are those who are truly negative, right, that may have a false positive test, and they're right here. I think I include that here. Sorry. And now the second part here is line C. And line C is representing a test with 100% specificity. So if we're talking about Western blot, line C, if we say this Western blot test has 100% specificity, it means 100% of the population who is truly negative for HIV gets a negative test result. So it accounts for everyone who is negative. But unfortunately, it may also account for some people who are truly positive. So it will give them a false negative result. So it will tell them, oh, you don't have HIV, but they do. So the most accurate and the best place that you want is line B. Okay, so this is where you want to be. And basically, this chart is great at explaining basically sensitivity versus specificity. And if you have a test that's 100% sensitive and 100% specific, and why that may not be the best thing, because it can accidentally leave in parts that are it leaves room for false positives and false negatives. And of course, this is like a perfect chart. So different tests, the lines will be in different areas. But this is just kind of the basic lines of where they are. Okay, so I'm going to talk about positive predictive value. So positive predictive value is used for tests that are sensitive. Obviously, not every test is going to be 100% sensitive, but they want to get as close as possible. So in this example, we're going to use the ELISA scan, which is our sensitivity test, and we're going to assume that it has 100% sensitivity rate. So again, 100% sensitivity, line A, everyone who's positive is taken into account. Okay, so you may have seen this table before. You have your population here of 1,000 people. Okay, in this column, 200 out of the 1,000 are HIV positive, and 800 out of the 1,000 are HIV negative. You take everyone and you do an ELISA scan on them. So the ELISA scan tells you 200 people are HIV positive. Okay, these are the true positives, and there's no negatives. So it's 200%. So a test, what you use something known as a positive predictive value, which is a measure of the probability that individuals with a positive test result truly have the condition or disease of interest. So how many people who tested positive are truly positive? And it has an equation. So you want to take the number of people who are truly positive, and you want to divide it by the sum of those who are truly positive plus those who are false positives. In this case, it's 200 over 200 plus 0, which is 200. So this test has a 100% positive predictive value. This is not a realistic example. I want to make a realistic example here. So again, similar circumstance, but in this case, 160 out of the 200 are HIV positive as detected by the ELISA scan, but 80 have been given a false positive test. In this case, how to calculate the positive predictive value is you take the true positive count, which is 160, and you divide it by the total that the ELISA scan has given a positive test result for, which is 160 plus 80, and that's 240. It means in this circumstance, the ELISA scan has a positive predictive value of 67%. So 67% of the people who test positive, 67% of all individuals testing positive are truly HIV positive. Okay, and in terms of the implications of this, this is what gives the clinician a lot of trust in the results of a test in terms of its sensitivity. And as you may have predicted, there is a negative predictive value, and this is for tests that are for specificity. So Western blot. Again, we're going to take an example where a Western blot has 100% specificity. Same population. In this case, no negatives, and everyone who has who's HIV negative has been correctly accounted for. In this case, the negative predictive value is 100%, which means if someone tests negative in this Western blot, you can be sure that they don't have HIV. This is a more realistic implication of it. So again, you have a Western blot test that identifies 720 out of the 800 who are HIV negative, but 40 have been given a false negative result. So you take the true negative and you plot that as your numerator, and you divide it by the total number of people who have been given a negative Western blot, okay? Whether it be HIV positive or negative. And that gives us a 95% score. And this is our negative predictive value. Okay. We're getting to the end of the presentation. We're almost there. Any questions so far? Okay. If you have any questions, let me know. All right, so this is quite straightforward. We have our mean, which is the average, and this is used to basically describe the average occurrence or severity of a disease within a population. So let's just say you have a certain population in Manchester over the age of 50, and you want to determine what's the average systolic blood pressure reading. So you're going to take 200 participants, you're going to measure their blood pressure, and you're going to take the systolic values and write them down. This is your collected data. So the average is you're going to add up all of these values, and you're going to divide them by the number of participants. And this is going to give you the average or the mean reading. So it tells you in Manchester, the average systolic blood pressure reading for adults or for individuals over the age of 50 is 142.4 millimeters of mercury. Median is basically where you have a set of data. Again, let's continue on with our example from here. So you have a set of data, you order them from the lowest blood pressure reading to the highest, and you try to figure out which is the middle, right? So the median is the middle reading. And this helps to determine, basically, it divides the data into two halves, okay? Those that are falling below and above the median. And the great thing about the median is that it's not influenced by extreme values or outliers, okay? Unlike the average. So if there's a reading here that's extremely low or extremely high or an outlier, it can definitely affect the average reading. But the median doesn't have that problem. It's not something that's concerning for it. So you find the middle number, but sometimes in the data you might have two numbers that are in the middle. So to determine the median, you take the average or the mean of the two middle values to determine what the median is. And lastly, we have the mode. The mode tells you what's the most frequently occurring value. So again, if you have these different systolic blood pressure readings in our population, we try to determine which one is the most frequently occurring. So after reading through the data, we may find that 130 millimeters of mercury occurs more than once in this data. So you can see it twice over here, which means it's more frequent than any other measurement, and this is known as the mode. We are running a little bit out of time, but I've put a few links over here and I can add them into the chat, which includes a little bit more information in terms of in epidemiology and statistics that you can have a quick read through. Be really helpful in terms of your research. So that's the end of our presentation. The last part is for tomorrow, and this is going to be our critically appraising section. And basically, it talks about how to go over the critical appraisal aspect of it and what tools are available to help you in this part. This should be a relatively short presentation. So it'll be a nice wrap up for our series. Again, the recordings for this presentation as well as the ones that were previously will be available on Medal. Don't forget to register for tomorrow's session and keep an eye out on for our Journal Club page on Mind the Bleep. And I look forward to seeing you guys. Don't forget to fill your feedback form and get your certificates. Before I end this, do you guys have any questions? Okay. All right. Okay, great. Thank you so much, everyone. Let me put the feedback form for you guys. And again, the more feedback, the better. Thank you, guys. Let me just post the feedback for you, and you can get the certificates. Thank you so much. Much appreciated. Thank you. Thank you guys so much. Okay. So I'll just put the feedback form for you guys. Thank you. Thank you. Take care. Have a good one.